Hello everyone, my name is Zhou. It's my pleasure to stand here to present our work on efficient page-level FTL to optimize address translation in flash memory. This is a joint work between HAS and VCU. Here is a list of authors. We will discuss our paper in 4 parts. In the first part, introduction, we will talk about the background and motivation. In the second part, we will talk about our solution. In the third part, we will evaluate our work, and in the last part, we conclude our work. Let's see the background first. NAND flash memory has gained increasing popularity in various markets due to high performance, low energy, and small size. Further, with the feature size scaling down and more bits stored in each flash cell, the per bit price is decreasing and the capacity is increasing. In contrast, the endurance and performance of flash memory are decreasing. For example, let's see this table. TLC has higher density than SLC, but undergoes less P cycles as well as longer write time and erase time. Flash memory shows different characteristics from hard disks. So, a flash translation layer called FTL is proposed to emulate a standard block device, and 2 major functions of the FTL are address translation, which translates a host logical address to a flash physical address, and garbage collection, which reclaims invalid pages. Page-level FTLs show better performance than block-level FTLs and hybrid FTLs. However, they suffer from larger pressure on address translation due to their large mapping table. This figure shows the architecture of a typical demand-based page-level FTL. And in this FTL, the whole mapping table is stored on flash memory in the form of translation pages. Each page contains hundreds of mapping entries, and multiple pages compose a translation block. And the mapping cache catches only a small number of active mapping entries. In addition, a global translation directory is cached to record the locations of translation pages on flash memory. When the requested entry is not cached, the FTL needs to read the entry from flash memory to the mapping cache, and if a dirty entry in the mapping cache is replaced, the FTL needs to write back the dirty entry from mapping cache to flash memory. So, address translation introduces extra operations which degrade the performance and lifetime of flash memory. To analyze the address translation overhead, we have developed 2 models, a performance model and a writebacks model. From these 2 models, we have 2 conclusions. First, address translation overhead comes from 2 aspects. First, cache loadings and replacements, and collecting translation blocks due to replacing dirty entries. The second, this overhead can be reduced by increasing the cache kill ratio or increasing the probability of replacing a dirty entry. If you are interested in our models, you can find more details in our paper. To investigate how to lower the probability of replacing a dirty entry, we have conducted experiments in DFTL, a typical demand-based page-level FTL, to study the distribution of cached dirty entries. A cached translation page refers to a translation page that has 1 or more entries being cached. We can see in the left figure, most cached translation pages have more than 130 entries being cached, and the average number of 30 entries in each cached translation page are larger than 15. This means that when replacements occur, most these translation pages will be updated on flash memory repeatedly, leading to significant replacement overhead. And to investigate how to increase the cache kill ratio, we have also conducted experiments to study the spatial locality in workloads. The right figure shows the number of cached translation pages And the red oval refers to a time period that some sequential accesses are happening. we can see that sequential accesses make the number of cache translation pages first decline and then rise back. This is because the entries required by sequential accesses focus on one or a few translation pages, while random accesses require dispersed entries in many translation pages. This observation can help us to recognize the sequential accesses in workloads. Based on these observations, we have these motivations. Inefficient cache management causes significant address translation overhead, degrading the performance and lifetime of flash memory. Moreover, existing FTL schemes suffer from different problems. DFTL leverages temporal locality to catch active mapping entries and does nothing to optimize dirty entry replacement and spatial locality exploitation. So, DFTL performs okay in random workloads and poorly in sequential workloads. SFTL leverages spatial locality to catch active compressed translation pages. Since a translation page contains hundreds of mapping entries whose logical page numbers are sequential, SFTL performs well in sequential workloads. However, it's not space efficient to catch an entire translation page in random workloads, so SFTL performs poorly in random workloads. So we need a new FTL that performs well in both random workloads and sequential workloads. Let's see our solution, TPFTL. TPFTL is a low demand-based page-level FTL with a translation page-level caching mechanism. This figure shows the architecture of TPFTL. Considering that the X unit of the mapping table on flash memory is a translation page, TPFTL clusters the cached mapping entries that belong to the same translation page in a virtual translation page node called TP node. In this figure, 11 mapping entries are clustered in 4 TP nodes. When a replacement occurs, TPFTL first chooses the coldest TP node and then the LRU mapping entry in the TP node as a victim. And the hotness of a TP node is decided by the average hotness of all its entries. This two-level LRU needs reveals the distribution of cached mapping entries, which can help us to design a workload-adaptive loading policy and an efficient replacement policy. In addition, a global translation directory is cached to record the locations of translation pages on flash memory, and a counter is maintained to record the number change of cached translation pages. They are necessary and take very small space. To increase the cache-hit ratio, we propose 2 prefetching techniques. First, request level prefetching exploits the sequential entity in each request. We know that for large I/O requests, the FTL first splits into multiple data page requests. TPFTL performs address translation on I/O request level rather than on page request level. Thus, each I/O request results in 1 cache miss at most. Let's see this figure. An I/O request with 15 sectors is split into 3 data page requests. Address translation on page request level leads 3 translation page reads to load the requested 3 mapping entries. And address translation on I/O request level needs only 1 page read to load the 3 requested mapping entries. In a workload with both random accesses and sequential accesses, small requests can be part of sequential accesses. So it's challenging to recognize the sequential accesses in workloads. We have observed that sequential accesses make the number of cached translation pages first decline and then rise back. This motivates us to propose selective prefetching and exploit the synchronity among requests. We set a threshold. When the number of cache translation pages decreases by a threshold, we assume that sequential accesses are happening, and TPFTL performs selective prefetching. And when the number of cache translation pages increases by a threshold, we assume sequential accesses are over, and the TPFTL stop perform selective prefetching. Let's see the figure. The left figure shows when to perform selective prefetching, and the threshold is set at 3. Further, the prefetching length is set as the number of cache predecessors. Let's see the right figure. It shows how to perform selective prefetching. The request entry has 2 cache predecessors marked in red. So the prefetching length is set as 2. Then, plus the requested one, 3 entries are going to be loaded into the mapping cache, and the requested one is put on the MRU location, and the prefetched 2 are put in the LRU locations. A high cache hit ratio is not enough to ensure no address translation overhead, because a high probability of replacing a dirty entry will need to significant address replacement overhead. So we propose 2 replacement techniques to lower the probability of replacing a dirty entry: batch update replacement and clean first replacement. Let's see this figure. 3 entries are going to be loaded into the cache, and the cache is full, so 3 entries in the coldest TP node TP5 are going to be effected. Clean first replacement postpones the replacement of dirty entries and prefers to choose clean entries as victims. So TPFTL first chooses the 2 clean entries in the TP5 as victims, and then the LRU dirty entry marked in green. These 3 entries are effected. Batch update replacement writes back all the dirty entries in a TP node when replacing one of the dirty entries in the TP nodes. So TPFTL writes back all the 3 dirty entries marked in red in TP5, evict them and write back the 3 dirty entries to flash memory. Further, in order not to sacrifice the cache hit ratio, only the victim dirty entry is effected, and the other 2 dirty entries remain in the cache and becomes clean. This replacement will not increase the replacement overhead, but reduces the number of cache dirty entries in a batch. Now let's see the evaluation. We evaluate TPFTL in FlashSim simulator and compare it to DFTL, SFTL, and the optimal FTL. The optimal FTL is a page-level FTL with infinite mapping cache that the whole mapping table can be cached. It's an ideal case for comparison. And the SSD configuration is shown in these 2 tables. In particular, the SSD size is set as large as the address space size of the workload. This means the SSD is in full use. And the cache size is set as large as the mapping table size of a block level FTL plus the GTD size. We use 4 enterprise workloads. Financial workloads are random dominant, and financial 1 is write dominant, financial 2 is read dominant. And MSR workloads are write dominant, but have much stronger sequentiality. We first evaluate the cache hit ratios and probabilities of replacing a dirty entry of the 4 FTLs. We can see in the left figure, TPFTL in red maintains relatively high hit ratios in all workloads. In financial workloads, TPFTL increases the catch key ratios by more than 10% compared to DFTL. And DFTL has slightly higher catch key ratios than SFTL. In MSR workloads, both TPFTL and SFTL have more than 95% catch key ratios, and DFTL falls behind. The right figure shows the probabilities of replacing a dirty entry of the full FTL. We can see that TPFTL significantly lowers the probability of replacing a dirty entry, and the probabilities are less than 4%, while the probabilities of DFTL and SFTL are larger than 50% in random write workloads, MSR workloads, and financial one workloads. These results show the efficiencies of the loading policy and the replacement policy of TPFTL. Higher catch key ratios lead to catch loadings and replacements. Lower probability of replacing a dirty entry leads to less writebacks of translation pages. So TPFTL achieves reductions on translation page reads and writes. And this table shows the results. The reason why the reductions on page reads are much smaller than the reductions on page writes compared to SFTL is because the replacement unit of SFTL is an entire translation page. So when writing back the translation page, SFTL does not need to read the page first. Then we evaluate the system response times and write amplifications of the 4 FTLs. Here, these reductions are not as dramatic as the catch key ratios and probabilities because the 4 FTLs share significant garbage collection overhead of data blocks. Let's see the figure. The gaps between the optimal FTL and the other FTLs show the significant address translation overhead, but we can see that TPFTL is still a step ahead of the other 2 FTLs. Although it's most challenging for flash memory to perform well in random write intensive workloads, TPFTL achieves the greatest advantages in financial one workload, a random write intensive workload, about 24% system response time reduction and 17% write amplification reduction compared to SFTL, and the DFTL performs slightly worse. In financial 2 workloads, TPFTL performs better than SFTL by about 9%. And in MSR workloads, both TPFTL and SFTL match the optimal FTL, and DFTL falls behind. These results shows TPFTL can reduce the system response time and the write amplifications, so improve the performance and lifetime of flash memory. Now let's conclude our work. Inefficient cache management results in significant address translation overhead, which degrades the performance and lifetime of flash memory. And this overhead can be reduced by increasing the cache key ratio or lowering the probability of replacing a dirty entry. To achieve these 2 goals, we propose TPFTL, which employs a 2-level cache mechanism with a workload-adaptive loading policy and an efficient replacement policy. And extensive evaluations with enterprise workloads shows that TPFTL can efficiently leverage a small mapping cache to perform fast address translation at low overhead. At last, we are grateful to our Sheffer, Microsoft, and the reviewers for their insightful feedback. That's all. Thanks for your listening. Any questions?